presentation is an extension of some of the last few years where Jeremiah presented, I think, 2 times in a row at the Energy Science Technology Conference in 2020 and 2021. We kind of flew under the radar of the COVID ban over at the Kootenai County Fairgrounds, and ever since then it's been becoming more compact, more efficient, putting out more power. You know, the whole goal is to make something practical out of these kind of things. Last year it was the plastic model, which basically demonstrated the concept just like this, a little bit smaller scale. It's taken a lot of work to get to this point.
So, bladeless turbine invented by Nikola Tesla. That's what the Tesla turbine was invented by. Based on the use of fluids of energy has been demonstrated. Okay, so I'll talk about the difference between the Tesla turbine and a regular turbine, a regular bladed turbine. And there's a lot of reasons why the Tesla turbine is a lot better and more efficient. So this is his patent. This is the basic Tesla turbine patent, and it's what everybody will go and they'll read this patent and they'll use these pictures to build their Tesla turbine. But the Tesla turbine here is an illustration. It's not. You can't copy this exactly and have a good Tesla turbine. There are some things in there that you can copy, and it would be an okay Tesla turbine, but you need a lot more disks. Okay, so I'm just going to add a little bit of compressed air here, and it'll start sucking up this water right here, this hot water, and it'll condense the water right here, and it'll come out really cold, and the energy will go into the turbine, into motive force. So you can see that spiral right there. That's what's going on in between the discs. Okay, so practical uses, there's a lot of different uses, and we're going to start with the first one and the most simple use. And that's just if you have a solar system in the wintertime and you don't want to buy a bunch of gas for your generator, if you don't want to be connected to the grid, you want a backup power system, if you have a wood stove and a solar system, you can charge your batteries in the wintertime with your wood stove when you're already burning the wood to keep your house warm. You can charge your batteries by heating your house. It's just a natural side effect. And there's nothing else on the market that can turn your wood stove, the heat from your wood stove, into electricity. You can use to heat your sand battery. Then you would take your sand battery and slowly heat your boiler when you want to make electricity to extract the power out of it. So we'd have our sand battery with a loop going through the boiler to heat the boiler. Then the boiler would produce your electricity, and you'd have a valve that would turn on and off based on the temperature drop on the boiler if it got too low. Yeah. Now, of course, this has got a smaller diameter, so it would be much easier to stop this than this. But you can hear the difference in the amount of power that comes out of it. And in our later videos, we will show the new completed turbine where we can actually do load tests and everything like that. I also have leaks coming out of here, so this isn't really a fair test. Again, 30 psi or 22 psi. cutting out the gaskets with a razor blade. It's not the safest way to do it. You should probably use a handle. Here's the rotor before we install the spacers. Here we show our Newman generator. Extremely simple, extremely powerful, high speed, extremely efficient. I know I'm saying extremely a lot, but it's what it is. Generator. So I will show you guys the thing running, and that will be the end of my presentation. Yeah. Oh. Thanks. So I'll name off the frequency when we get to a certain speed, and then you just multiply any number, the hertz, because the magnet is, there's a frequency showing on the meter based on the speed of the rotor. Okay, so now we're about almost 5 psi, because we let a lot of heat through, and we lost a little bit of pressure because it's just letting the gas go straight through right now. So we're going 50. I'm going to get my calculator out here so I can. So 50 times 60. We're going 3,000 RPM right now. And that's what 3,000 RPM sounds like. $6,000 RPM. 12,000 RPM. $18,000 RPM. I'm not sure what that is. 24,000 RPM. So that's still really, really low on the low end. I got to turn the valve down. I got to turn it down a little bit because we don't want it to go any faster yet. But you can see it's really quiet for how fast it's going.
What's the temperature?
The temperature of the it's at 0 degrees or 0 psi on the boiler. So it's 212 degrees because that's the atmospheric pressure. So
Lower than boiling point.
Yeah. $400. Okay, 24,000 RPM. I just don't want it to go too high. That's why I'm turning off these valves. But it's so quiet.
Are you sure it's running? I can't hear anything.
Okay, this is run number 2 with the extra air vacuumed out of the system.
Yeah.
What pressure is it at?
It's at 20 psi.
So that's
260 degrees.
260.
And the condenser is at 13.5.
Okay, you got an extra meter here. You're gonna be reading
it's a voltmeter, but that's mostly just for me.
and then
I'll name it off if I have a chance.
okay.
Well, yeah, when
And
it's
the watt
spinning,
meter.
you can come up and take a look. Okay.
Okay, read off the RPMs.
Or 18 or 12,000.
12,000.
Vacuum is looking good. 18,000.
Yep.
Hertz. 500 hertz. 550, 560, 580, 590. See? It's not hitting the sidewall anymore. 670.
So that sounds like that's your maximum RPM right now.
Was that 1200 or so?
680 when it started going.
No, watts. What was the max that
It was like 1300 watts.